So this is 2160, the lecture 23 already, the Gaussian processes. So, this is a little challenging and stuff. So, let me just make some simple case. And this is to explain the Gaussian processes in a nutshell. So suppose, you have 3 points and 4 points and just a few points as plotted here and an XY plane. And you respect these points, which are very variable measurements, and we respect these. You don't want to draw just a straight line here, but I know it's not clear. Should I use a quadratic function, a cubic? It's not so much clear. It's better if we have something that's going to a nonlinear relationship, but it's a non-parametric. A Gaussian process is a non-parametric nonlinear regression, providing some stochastic model. So yeah, we have some training data, and we trained the Gaussian process to fit those actual training data points. And then we ask ourselves, what if I got the new pointer here, X star, we call this a test point, and usually in machine learning, we put the star here, which is actually, some new point we'd like to investigate, and then we'll try to find the corresponding output, to say Y star, right? So that is something what we like to do. So this is nothing but the regression. It is a stochastic regression and a non-parametric, okay? And then, of course, we can deal with some nonlinear relationship. Now, so let's think about it this way. So if we have already observed the point A, B, C, D, and then we really respect these points, and the new point we'd like to investigate, to say X star, is very close to a point XC in input space, then this output would be somewhat very close to the corresponding output YC. As X star gets far from this XC, then it may be more away from YC. And then more importantly, as we are away from this point XC, things are more uncertain, right? I just sketched the yellow, this shadow area. It's to be something possible, data, possible points in, response to X star and the other points. So determining the expected values, let's say in a mean value, as well as some kind of variance, that whole depends on the points here, and then how far it is from the known points. And we should include not only the C, which is closest, but a little bit, distal point to D and B and even A should have some kind of influence upon determining the distributions of the point corresponding to X star, right? So the Gaussian process regression can deal with this kind of situation in a very systematic way. This Gaussian process, a little bit on historical background, it came from mining, basically. It is actually the field called geostatistics. It's a particular branch of statistics dealing with some spatial and spatial temporal data, okay? So, suppose you want to actually find some, let's say, petroleum, resource, and you dig a few points over here, and then you get this, at a certain location along this x-axis, you dig it here and here, and you get to some result here and here, right? Now you ask yourself, what if I dig here? What is the possibility of getting the kind of good results, or what is the in terms of this metric y, what is actually expected value for that? So this is a kind of stuff being done in the so-called petroleum geology, hydrogeology. And then, even more interesting is that going to a 2D, such as this case, it's not just a one, directional, distribution, but, we need to deal with the two-dimensional distribution, sometimes the 3D. Well, in dealing with, for instance, oceanography, and then our environment control program, environment issues, we need to actually expand it to this space. And it's being done quite extensively by using this theory, Gaussian processes. In our actually 2160, the focal points, both machine learning and some system dynamics and controls, they are using this theory, Gaussian process, into their areas. So, oops, I should put this one this way. Sorry about that. Okay, and for machine learning, this is obviously a useful, tools. It is actually, kind of input-output regression, and a non-parametric, and then we can deal with the nonlinear curve over here. So given a certain number of training points, we like to predict an output mean and covariance. Not just telling that this is the point I pick, and instead we can say this is most likely with the variances, or confidence intervals of such and such. System identification control area. This could be used more, but some of the interesting attempts have been made. And in the last, since the late 90s, there's a significant increase of the publications on this topic. So, Gaussian process model itself is a non-parametric and a non-linear and a stochastic model, right? Combine this one with some known knowledge about the input-output dynamical systems, what are inputs, what are outputs, what are the type of input sequence that's relevant to determine the output. Maybe we can actually combine this and say with the ARX model, autoregressive with the exogenous input model. So we have, you remember that the autoregressive part, and YT equal minus A1 times YT minus 1, and minus A sub 2 times YT minus 2, right? And also input sequence part 2 is involved. And then actually some noise is actually added to that. Then you get the observed output and predictions in Y hat, right? So that's actually the models we can use. And if you put this into not just the linear, equations, as I said, YT equal minus A1, YT minus 1, that's actually linear, ARX. But if you combine that one with the Gaussian process model, it's going to be a nonlinear ARX model. It's called the GP and ARX, and then that's actually the one and the model that people used. Other areas, this Gaussian process models are being combined with a Kalman filter, a Bayes filter in particular, and then more recently it is applied to a unscented Kalman filter. It is to produce a very interesting results, which is to supplement some of the program of previous methods. So that's actually a quick overview. And then I like to show some of the essence of this theory. Now, suppose we have two random variables, x1 and then x2, okay? And they are jointly Gaussian. What that means is that if you pick the x1, x2 probability density, it is given by this kind of expressions where you can see that sigma is the covariance matrix and sandwiched by x1, x2, and x1, x2 from both sides. And then that's part of the exponential functions, right? So, if sigma takes this values, the cross correlation between x1 and x2, this part is 0.8. If this is the case, the kind of ellipse associated with this normal two variate Gaussian distribution can be represented by this kind of ellipse, right? So now interesting question is this. Suppose that an x1 equal a is just observed, okay? Now, knowing the value of x1 tells us something about the value of y2 because x1, x2 are correlated in here, right? So this one is basically conditional probability. Given x1, what is the chances of having an x2? That's actually p x2 slash x1, right? Yeah, and interestingly, so as actually, I just cut this part, here, at this point x1 equal to a, and look at the distributions of, x2 along this line, and it turns out to be something like this kind of curve. And interestingly, the conditional the distribution, this guy, is also Gaussian, which is completely described by its mean value, mu star, actually corresponding to some new test point, okay? And then actually, variance or standard deviation on, the sigma star in here. Now, let me show you some counterexample. If instead, the x1, x2 are not correlated, like this, and 0, 0 in here, okay? So putting this one into this, this term becomes x1 square plus x2 square, right? So exponential can be split into two terms. So it turns out this joint Gaussian probability can be, decomposed to px1 and px2. It is basically independent of these two. So even though you get the value of x1, it doesn't help to predict the x2, right? So as you can see here, this is a case, a pure circle case, and I cut it at the line x1 equal a. You get some distribution. See, this one is completely symmetric, and it doesn't actually, mean value doesn't shift in any directions. So that agrees with our observation. This is actually independent. So conditional doesn't mean anything. So depending on how these 2 points, x1 and x2 are related, as explained here, we can actually estimate by knowing one side how much we can know the other side. This can be extended to do. Let's say that we pick 5 variables, random variables, x1 to x5, and I created the joint Gaussian with this covariance matrix, and between x1 and x2 we have a correlation of 0.9, strong correlations. Between x1 and x3 it's a little bit lower, 0.7, and far end from here to here no correlation in this particular example. Okay. So, so this is a kind of simple extension from 2D to say in this case to 5 dimensional ones. How about the situation where this x value, although I picked the specific x1, x2, x5 in here, but this one is densely continually line up over here. Maybe we can put all the lengthy vector x1, x2, x3, density populated here. We can put in there, but at the end of the day, we can think about the uncountable infinite number of random variables. What comes into your mind? You have infinite dimension of the vector over here, right? That's basically going to Hilbert space. So instead of using an index 1, 2, 3, we use a variable x, which takes a continuous real number, and then that's going to kind of function of x. X is actually indexing variable But I know we extend it to a continuous number, okay? And then it becomes a Hilbert space. So definitions of Gaussian process. Gaussian process is a type of random process because remember that it's a kind of collections of random variables, right? Along this line, if this were the timeline, which was actually the process we discussed a lot in the past case, but I know this horizontal axis is not necessarily time, but it can be any variable such as the displacement in the x or multidimensional indices, right? Or continuous variables. So this is it's interesting extension to spatial and spatial temporal relationship. It is a collection of random variables, and if you pick any finite number of the random variables from this random process, it shows a joint Gaussian distribution, just as we did. Okay, so suppose this is a continuous number, and then you pick a particular point in the x1, x2, x something, and then putting it there into a vector, which is in this case finite, right? You can actually create the kind of normal Gaussian distribution with the mean value mu and the covariance sigma, right? Now, now what we like to do is not just dealing with the points which we observed and then actually use here, but the data. But we like to predict something new, right? So we put them together into some the data points which are basically training data points, and then something we like to investigate, test points. And then as before, we put the test points into this F star, and then F is something that we have already observed. For this extended one, we can actually create the normal distribution with the mean values and the covariance matrices. And then I just put this one, CC transpose both sides, and then sigma star having the appropriate dimensions. So sigma is associated with the F, and then sigma star is also associated with the F star. Okay. Now with this, the key mathematical tools is the following. So before taking any data, okay, any data. Okay, well, but perhaps you just pick these points and then create this normal distribution, right? So this one is basically before training the this Gaussian process with a particular set of the data points. It has some original, or I would say prior distribution represented by this means and covariance matrix. Okay, now suppose that the F, okay, this part F have been observed, and then based on that observation, let's find the F star. Okay, so these are unknown part. Okay, namely, obtain the conditional distribution of F star conditioned by observation F. So we write it in this way. Okay, we call this the posterior distribution. So you can think about something we did the Gaussian, Bayesian filter or Kalman filter. We all talk about the a posteriori versus a posteriori. Here the prior versus the posterior distributions. Okay, so this is after we observe this. Okay, now this can be obtained by using the following. It's called the Gaussian identity. Yeah, this is very well-known identity, and you can find it in many textbooks. We'd have to just use it, and we just address this from a little bit different viewpoint later. But let's use this. Okay, so this is nothing but to obtain conditional distribution of this guy, and if from this prior distributions. Okay, and once this one is conditioned by F, this is changed to this. it's again the Gaussian distribution, as I showed you the example before, and having this mean value and then the variance of this part, this matrix. Oftentimes we formulate the problem so that the priors having a 0, 0 mean values. So mu equals 0, mu star is 0. So substituting that one into there. So this is the most often used expression. So it has the mean values here and then covariance here. So after you learn something about the this part, inside of it, you have a pair of x1, y1, x2, y2, and a bunch of data points involved here. And after you learn that, the mean values for x star corresponds to f star is actually shifting to this point, which is proportional to the learned the data points, output the data points f. And the more interesting part is this covariance part, covariance part. Covariance I just rewrote in here, okay? And then sigma star is the one corresponding to f star, which is actually in the prior covariance, prior distributions, and this is the variance for that. So before you learn these training data points, our original distributions and having this covariance, okay? That is this guy. And actually, after you learned this, condition this, it is to reduce to this one. So this particular second term minus C transpose sigma inverse C, which comes from this C and then this sigma, okay, is to be subtracted from prior covariance. So basically, after you trained it, posterior variance reduces the prior covariance. Okay, so this second part, the reduction in uncertainty due to observations we trained. Okay, so at the end of the day, you get this kind of a curve. So you have some mean value, which is actually determined by this expression, and also you have a covariance. Originally, this distribution, now it is reduced to this. So these are all found depends on the sample points, training points, x1, x2. All these points are embedded here. Okay, so sigma is reflecting that. So this is part of a PS number 6, problem 3C, and I want you to draw this line, the mean value. And then, confidence intervals, let's say 95 confidence intervals, it's about the plus minus 2 sigma of the confidence intervals. That's the stuff, I want you to do it. So after this point, it's very quick, easy, part. And I'd like to entertain any questions. If you have anything to clarify. Yeah, after this, we go to a little heavy math. And so you get to some sense, right? So we basically assume joint Gaussian distribution, okay? And that's the main framework of this. And then we know, how much we can actually estimate a certain point given those certain points. And this method is quite useful. In particular, you have not many data points, and experiments are very expensive. Drilling the wells is very expensive, so you don't have many data points, but you should be able to maximize the information you obtained through just a few points of observations. That's actually this one fits very well. Okay, yeah. And I go to the next part, which is a little bit a challenge. And then just stop me if you have any questions anytime. Okay, so let's go back to the theory. So I'd like to first explain the kind of outlines or roadmap, how we can improve the everything. So first the program formulations. And, in addition to the previous point, we did it to some extent, but the noise must be considered in observation, right? We formulate the following noise corrupted observation, Y. Okay, Y is this actually Gaussian process part, plus actually some noise comes in when you observe the output Y. Okay, and then this actually, a noise is also Gaussian and with zero mean, and sigma n is a the deviations. Okay, now we use the data matrix as in the case of any other machine learning and supervised learning. So we have a set of data x1 to xn, and then in the y side you can think about some scalar output and then expand it later, just a scalar output and y1 to yn, put in this way. And please note that both epsilon and the f are random variables. Yeah, the f is a random process, indexed with x. So when I write this, don't actually misunderstand that, hey, this part fx is a deterministic part plus some random part. No. Okay, both epsilon and then fx is actually random. Fx is a random process. Okay, so that's a little bit complicated, and it's a little difficult to conceive. Basically, this is the Hilbert space, infinite dimensional vector, and having some randomness. So that's a little difficult to think. So, and we take the little bit of detour, but this is easy to understand. So let's suppose just first step. Fx is given by just a linear regression with the weight w. So x transpose w is to give fx. Okay. Unlike the just a standard case, and this w is basically random variables. We treat this one as random variables. Okay. Therefore, f becomes random. Okay. Now doing this, actually, we don't just stop it, doing this with just linear regression. Instead, the end result of this guy, the linear regression, turns out to be chronal. And actually, x shows up, x transpose x, and then all the way to some kind of quadratic forms comes out. And then that's actually, positive but definite ones. So we can actually replace XX transpose and something similar to that by kernels. So we studied kernel last time, right? And a very powerful tool. So sometimes actually this one is to expand the original input space X to infinite dimensional feature space. So that's the power of kernels. Okay. So that's a way by using this kernel. So we relate this one to Hilbert space. Finally, we will obtain a general case, which is non-parametric. And non-parametric means that we abandoned this kind of a particular linear regression structure. We're going to non-parametric regime, and that's actually dealt with in the Hilbert space. Okay, so let's start with the simple case. We assume the linear regression like this kind of form, right? And then the observation, however, comes with this noise epsilon. Okay, and then this is the the data we use. Consider the probability of observing y given a weight vector w and input x. What is the probability of observing y? So that's actually probability of y given x and w. Okay, the only random variables is epsilon in this case because in this conditional and probability, w2 is actually given. Okay, then look at the y. So the stochasticity of y comes from epsilon, this epsilon alone. Okay, and then epsilon is assumed to be independent and identically distributed IID. Therefore, this conditional probability can be represented by this product of probabilities, meaning that probability of y1 is observed in response to x1 and the given w times probability of y2 given x2 when the parameter is w. And then that's a product is to give this probability, right? And then now we look at the yi, and then these are given. So only probabilistic part is on the epsilon. So epsilon is y minus fx. So in y, probability comes from this form. Oops, this form. So we put in here and replace this guy in this way. Now all exponential product putting into inside of exponential, it becomes a summation. That's very convenient, right? And then this particular part can be written in a more simple vector matrix form by using a capital Y and a capital X in this way, right? And I just get rid of a coefficient here, which is not so much important. So this probability given capital X and the W, probability of Y is normal distribution and with the mean value, this guy X transpose W, and then this is the variance, and I is an identity matrix. Okay, now so let's see. Yeah, our objective is to obtain the distributions of function f, right? F. Which depends on the weight vectors W. So yeah, we look at only the first half, but our main objective is to characterize and then the random process F, and that's basically done with this regressions in this particular simpler case. So let's also obtain the distribution of weight W, which is to be determined from the data, D. And then we apply the Bayesian inference. I mean, that's actually based on the Bayes rules, right? So, as I said, the W is treated as a stochastic, quantities. So assuming that the prior of weight distribution is zero mean Gaussian. So this is a little bit a difficult part to provide any meaningful ones. But before doing anything, so let's assume that the weight W is distributed. And then we know just a rough estimate of their variance. It's to be sigma p. Sigma p is actually covariance of the W, which is normally distributed, zero mean. Zero mean is actually a reasonable assumption. But in some way we actually provide the sigma p, okay, sigma p. And definition is this guy. And so probability distribution of the W is given by this normal distributions, right? So what we'd like to do is actually put these two things, A and B, we obtained. So now we put together, we apply the Bayes rule. So the Bayes rule is Pxy equal Pyx Px over Py. Remember that, right? So right hand side we have likelihood function, Pyx. If x is a case, what is actually probability of observation y, and then prior Px, right? So replacing so applying this one to our case, let's replace x by w, because w is something we like to predict, right? W is something we like to predict. And on y is small y in here is our large y, basically data, okay? So what we can apply this one to this is our objective. We like to obtain the probability of W conditioned by our data, okay? Y and X are actually training data. With the training data, what is the distribution of W? W is originally distributed in this way, this way, but by using the training data, X and W, it is to be changed, right? And by using this Bayes rule, it can be written as, say, probability of W, which is actually prior, this guy, and actually putting W, downstairs, Y, conditioned by X and the W is to give this one, right? So that is actually Bayes rules application to this. So what is this guy? probability of y given x and w. This is one we obtained previously. This guy, PYXW. So this is actually, this is the final result, result A, right? Result A. And then this part, PW, is something we obtained, we modeled here. So let's put them together into this. So, we have a, product of two exponentials, we add these, argument part together. And this one is quadratic form with respect to W. So highest order, W transpose W, W transpose W, involved in these two terms. So let's put them together. And actually the remaining part is the first order of W and then constant, right? But first of all, this constant term, we can actually kick out this guy. This is a known ones and nothing probabilistic. So we can just, this is actually exponential of y transpose y comes out of this expression that serves as a kind of scalar over here, which is not our interest. So just kick out that one. The remaining part is actually this quadratic, second order, the WW transpose, and then actually single order W. And then we can put together these two and then create the matrix A, which is picking up this XX transpose and divided by sigma n. And here it's a sigma P inverse, which is actually an original covariance of the W itself, and put it together and then define the matrix A, which is basically the key part of this quadratic form. Okay. And then we have some, first order term, the remaining part. And so we put it in this way, minus W bar, not minus W bar. Comparing these two terms, we can determine what the W bar means, taking from here. And actually, this is actually, first order part, taken from both sides. And then this one equating this must be held for all W. And then the W hat bar is to be determined in this way. So this is actually full distributions of this conditional probability of W after you use the training data XY. The probability distribution of W is given by this. It's a little bit different from the just a standard D square estimate, but we assume the distribution of W in this way. So this is a stochastic treatment. Okay. So with that, we can actually, conclude this, case. Output the prediction in response to test point input, the new point in X star, which is not involved in the original training sample. So in summary, given some data, X, Y, with noisy observation, okay, so noise is involved here. The posterior distribution of parameter W, which posterior means that after you incorporate the training data, and such, and distribution is also Gaussian distribution with the following the mean and the covariance. So, this is the mean and this is the covariance as we obtained, from the previous, derivation. So given that, so this is the model we obtain based on the training data, right? So with this, now we like to test how it is to predict the output Y in response to X star. X star is given. What is the expected output? So that this is the case, right? Please note that both W and the epsilon are random variables again. Okay, output Y star can be reached through many combination of W and then epsilon values. So it's going to Chapman-Kolmogorov equations. You remember that we did it some time ago. So we have we like to estimate the predictions. Predictive distribution of Y hat in response to X star, which is actually in a product with W. So the way we start is first we start with the X and Y, the data, which is to determine W, and then for the W, we can actually determine Y. But this one is all probabilistic. So we have to take many routes from here to some value of W and then end up with something here, right? And in the other case, W take the different value and then some route that we arrive at this. So remember, that's the things that we did. So this is actually in a Chapman-Kolmogorov. We multiply these two. So this guy is given XY, what is the probability of W? That is this probability is given by this part. And then this one is given W and then a new X star, and then we like to predict this guy. So this one, the W to this Y transition. So we multiply these two and then take a summation, and integration. The computation a little bit messy, but it's just a standard textbook materials. And then the end result is something like this. So probability distribution of the predicted output Y given training data XY and then given the test point X star is a normal distribution with the mean value X star and transpose W bar. This makes sense, right? This is mean is basically means of W times X star. That's actually standard. But the more interesting point is that the X star transpose A inverse X and X star is the posterior covariance evaluation, which is actually smaller than the previous one. Okay, so now after this point, we discussed just are you tired already? I'm not sure. So after this point, we just use the linear regression. Okay, that's actually not our goal, right? But linear regressions, if you look at that more carefully, we have a chance to use a kernel. And then kernel is great because sometimes the kernel can map the infinite dimensional input to infinite dimensional feature vectors, right? So we use that technique from this point. Okay. So okay, kernel trick. So far we use a linear parametric model, but the input X can be projected to our high dimensional feature space. The kernel trick is applicable to Gaussian process. Okay. So, what we do is basically we replace this X by function phi. Phi is, phi is something like this, original, input is just x1 to xn, finite dimensional, n-dimensional, vector. But with phi, this can be expanded to m-dimensional, and then sometimes m is infinitely large, right? So that's actually kernels. Okay, so we replace this x by this expanded feature function phi of x, and then do the same of the derivations, just as we did for the linear regression. Okay. Now, for the sake of simplicity, function phi evaluated at the point x1 to xn can be put together into capital phi of capital X, right? So if we do the same thing, the end result is nothing but the replacement of the previous equations. So, mean part is this one was originally X, is now, phi of X star. Excuse me, X star is now replaced by phi X star. And then, A inverse phi is also, coming from here, right? And the Y. And then, so this is actually, previously X star transpose A inverse X star. Okay, now it is expanded in this way. So the matrix A is actually, we did this replacement some time ago. yeah, this part is now expanded to this, phi, capital phi x transpose. So, in this way, we can surely expand the space very nicely. Now, there's one interesting, important point to mention, and there's an interesting trick. So one drawback of the above nonlinear regression based on the Gaussian process using this kernel function is that it entails the inversion of matrix A, which can be of high dimension, or worst case, it's infinite dimensions, right? So A equal this something like this. This is m-dimensional vectors, right? M-dimensional matrix, excuse me, right? So inversion of m by m matrix, however, can be reduced to the inversion of n by n matrix. The n is the number of sample points and the data points. It's not actually infinite, right? And we can use the following kind of trick. So we defined this matrix K. It sounds kernel. In fact, it is type of kernel later. But for the time being, K is just actually defined to be like this. Okay. Remember, psi x is the one that actually specific phi function phi x1, phi x2. These are all involved line up over here. Okay. We use a capital phi. Okay. Now let's actually consider this function. Don't ask why we consider this. You find it later. Okay, just consider this expression and then replace k by this. It becomes this one, right? I just replace k by this expression by definition. Okay, and then let's actually distribute this one to this and to this. So first term phi transpose sigma p phi and then phi. Okay, and if you look at this part, since the definitions of A is this, so this part is A minus sigma P inverse, right? So that I put in here, A minus sigma P inverse times, this part. And then again, distributing this one in here and here, you get the A sigma P phi. And from here, sigma p inverse sigma p cancel out, so leaving only phi, and then put in this phi, so these two cancel out. At the end, we have A sigma p phi. Okay, so this length expression turns out to be this guy. Now, we continue this. So what we found is this expression end up with this, right? Pre-multiply A inverse and then post-multiply this inverse. So left-hand side becomes 1 over sigma n squared and pre-multiplying A inverse and then post-multiplying this guy disappeared. So A inverse phi equals A and then this inverse comes out from both sides, okay? Now, if you check the dimension of the matrix inversion, left-hand side is basically A matrix, so original m by m matrix inversion is needed here. But the right-hand side, if you see the matrix inversion must be taken for this one, which is actually n, capital N by n dimensional matrix. And then this one is basically the number of data points. So data points are not that many, say 200, 300, it's more manageable. Compared to the expanded feature space and almost infinitely large, this one is significantly lower dimensional. So we can successfully eliminate the high dimensional inversion to low dimensional inversion in this. So this trick is needed. Okay,
Professor Asada?
Sure, go ahead.
Why do we have that A term on the right-hand side? Should that have been canceled out by the pre-multiplying by A inverse?
Oops. Let me see. Yeah, that's a mistake. It's a stupid mistake. Why did I make this mistake? Oh, yeah. This one is, oh my goodness, this is the horrible the typos. Thank you, Charles. Yeah. So, yeah, we want to kill this guy. So A inverse is multiplied to this. So this one we can kick out this guy. Right. That's right. Right. Otherwise, no. Yeah, I use the same equation over here. So, my goodness. I hope I won't propagate that mistake further. Yeah, here A is actually disappeared. So, yeah. Okay. So, sorry, I'll just post the corrected version. Yeah, thank you. Okay, the continuing. So I know this part is now replaced by this, and so this one should be eliminated. The covariance of the posterior can be reduced by using. Oh, okay. So this is actually mean part, right? The mean part is involved in this expression, this mean part. Yeah, this mean part. And then now this part. This is a covariance part, also includes the A inverse, and we need to replace it by something low dimensional ones. And for this one, we use the matrix inversion lemma along with the above trick. And then let me just show the end result alone. This is nothing but matrix inversion lemma. It turns out the two terms comes out, and then it has a pretty clear physical sense, in here. But the two terms comes out. But the more important point is basically kernels, involved in this, expression. So we obtained just, predictive posteriori distribution of the output in response to input X star, and then that is given by this, right? And given by this. And then now, sorry about this A, I have to correct that. Yeah, now this guy, if you examine this more carefully, again, the phi star is actually, phi evaluated at this X, right? And then capital X is also, phi in here, right? So in the above expression, phi star and then phi xi show up always in a quadratic form, like this kind of form. Let's check out this guy, right? So the A is actually a typo, and sorry about that. And then inside of this big psi, big phi, we have a small phi here, right? So it is actually, this term too, it's a kind of sandwiching this, sigma p with the small phi star and then the phi x something. So bunch of that actually quadratic form is involved in here. And look at here too. This is actually quadratic form, right? And here phi is here. So this part quadratic form, and this is quadratic forms, right? So all of these actually expressions shows up in phi and phi xi in a quadratic form. Okay, and actually, please note that the sandwiching this one is basically a sigma p, which is a prior distributions of parameter w. It's basically the covariance matrix, which is absolutely positive definite, right? Positive definite. Okay, so this is the original definition. Expectation of WW transpose is a positive definite and symmetric matrix. Therefore, we can actually find a kernel. Kernel does exist. So this quadratic form can be reduced to some inner product of some new variables, psi and psi x prime. We can actually reduce this one into this form. Okay. Now, proof is by construction, and we can do the following technique. So first, let's actually decompose this sigma p, which is a positive definite, can be decomposed to VDV transpose. The V is what? These are eigenvalues of this matrix, psi, the sigma p. And this is positive definite, so all sigmas are basically lambda, excuse me, lambda is positive, and associated with these eigenvalues, eigenvectors can be placed in this way, right? So, what we need to do is to reduce this one into this inner product form, right? So what you do is to apply that, square root matrix. We did this in somewhere, right? Twice, most recently we did it in the subspace method part, right? So because all sigmas are non-negative, so we can take the square root of it, right? And then take the part of that decomposition, and then half of them is put into this, and half of them the other part. So this one, sigma p, is now decomposed to V, and the D transpose, and now D is half, put in this side, and half put in this side, square root of them, I put in this one to this side. And we define this as a new function phi, denoted the psi x, and then psi x prime. And you can see this one is inner product, because it's just a transpose and then the original matrix vectors. So this is nothing but the inner product, right? So kernel function is defined for the covariance matrix. So covariance matrix and kernels almost synonyms. Covariance matrix by definition, it is symmetric and positive definite, right? So we can always actually, reduce that to, kernel functions like this, kernel function. This is very important and interesting part. And this type of kernel is called the covariance kernels, associated with the covariance matrix. If an algorithm is given solely in terms of the inner product, like this kernels, the kernel is more important than the corresponding feature space, phi x and psi x, which may be actually infinite dimensional and then cannot compute, but as far as you use a kernel, it's all set. So, here's the, main point. So, Gaussian process can be addressed in Hilbert space, functional space. The posterior, distributions of output has been obtained for the parametric models, right? So we started with this, right? Originally X transpose W, and then expanded to phi, right? That's the kind of historical things that we did, today. However, the mean and variance of the posterior distribution can be written with respect to covariance kernels, K, where the expanded features in phi X are not explicitly involved, right? Not explicit. This one may be a high dimension, not explicitly involved. So we put in the low key. We focus on the kernel K. This allows us to represent and analyze the Gaussian processes without the use of parametric models. We don't have to go back to this parametric model W, but we start with this kernel. Then it's all set. No matter where this one comes from, parametric model or non-parametric, we don't care. But as far as the covariance is given by this kernel, so that's fine. Instead, exploiting the kernels, we can formulate the Gaussian process directly in the function space, where a kernel that is actually in a product is defined. Namely, Gaussian processes are defined in Hilbert space. It can be in an infinite dimensional space. So Gaussian process is completely specified by its mean and the covariance, right? And the covariance is, i.e., that's a kernel. So mean is actually this process, mean, and then actually covariance is, this actually Gaussian process F minus M. Remember that the F is actually random process, okay, random variables, each of them, right? Minus M, and then it's actually paired. This one is given by the kernel functions. Then we write the Gaussian process. So this is something that you see some papers, the literature. Fx is basically GP with the mean M and then kernel covariance XX, right? So Gaussian process in Hilbert space. So if you just go back to the original point we did, what we did was starting with the parametric representations, and but the mean value is 0, as well as set this guy to 0, right? And then going through this, we started with this, putting this one back to back, and then WW transpose is involved, and this one end up with the sigma p, right? And then we showed how this one can be, reduced to a, inner product of new functions, and then that's nothing but the kernel. Okay, so note the parameter W is a mean 0, and then covariance is a kernel, and then covariance is a kernel function. Oftentimes the mean of Gaussian process is set to be 0. So mean is, we can deal with it in some other way. So original process is shown simply by this. The above argument is, implies that the mean and the covariance, the two quantities that completely characterize the Gaussian process, can be represented without the use of feature vectors. So this is a very important point. I'm just emphasizing this again. Okay, for any finite number of input variables, even though the original ones are actually infinite dimensionals, but you can pick any samples x1 to xn, and the n by n covariance matrix can be formulated with the kernel functions. So so remember that the Gaussian process is you can pick any finite number of samples from there, and then you can form that the sample data, say capital X, x1, xn. For that, we can actually formulate the covariance matrix, because covariance matrix is basically kernel. So don't go through phi, go directly from X to kernel X, kernel K. That's actually a kernel function of this. Okay, so now, and we use this radial basis functions. How many times have we encountered radial basis functions? At least 4 or 5 times, right? But it's good to repeatedly, visit this, because this is so important and so useful. And then, Gaussian process too, we use this. Okay, so this is, there are many other kernel functions, okay? But this is one most widely used. And we use this guy with a little bit slightly different parameter L. When we created the function approximations, we use beta. Now it's a little bit different parameter L. And L represents the characteristic length scale. So if L is large, it covers a wider range, and if L is small, the smaller range. This is something that kind of hyperparameter you can tune depending on your needs. Okay? One interesting property is of this guy is f x equal x prime. These two are the same. So x prime is usually center point, right? So and x is actually on top of the center point. The distance is 0. Then these 2 points are closest, and then actually the value of this kernel is 1. Okay. So as a characteristic length scale, note that this kernel can be decomposed to the inner product of feature vectors, but the vector is actually infinite dimensions, as we discussed previously in Kernel Trick. We do not care the original feature vector phi x, but we just use this kind of stuff. And then I'm saying this once again because remember that the last time we decompose the kernel this radial basis function kernels into 2 vector products. Remember that? And it turns out that this exponential divided into 2 parts, which are basically inner product. It turns out that the phi x was actually what? Infinite dimensional. Remember that? Infinite dimensional, because we expanded by using Taylor series expansion, exponentials and expanded, and then we put it into 2 parts to separate x versus x prime. and it turns out that each phi x is infinite dimensional, right? But I know we just keep it in this kernel form. We don't have to worry about that kind of situations. Okay, now this is the final important part, the mathematical tools, and I hope you can master. Let's start with the simple case in a noise-free observation. So we had two stochasticity. One is actually stochasticity randomness of the Gaussian process itself, function f, right? The other is actually observation part of randomness. Let's put the observation part of randomness. Noise is to be 0. Okay, noise to be 0. So with that, we can make the following argument, and then we immediately expand it later to a noisy case. So our interest is to predict an output in response to a set of test input. This doesn't have to be a single point, or maybe a multiple point, and then put into a capital X star. With the Gaussian process tuned to a specific training data, X and then Y. First, let us consider the case where observations are noiseless, noise-free. The covariance matrix of the Gaussian process associated with the input, the X and the X star, can be written as a block symmetric matrix of kernel functions. So this is the one I showed you in a nutshell version. So from there's actually X is actually a real number, continuous number. We pick some samples, so x1 to xn, right? For that, we can evaluate the kernel values, and we put them into the matrix form by taking the all combination in a type of gram matrix. You remember that one? We did it in the last Monday. So we use the same type of kernel matrix as arranged for this X and then X star. It's going to block. Okay, each of this X say K XX is basically in this case capital N by N matrix, capital N by N matrix. And if you want to examine capital N star and the test points, this particular part of a matrix, it becomes N star times N star matrix. And then this off diagonal terms have the consistent dimensions. Okay, so this is actually kind of manifestations of kernel functions evaluated at those points of interest. Okay. Now the prediction of fx star, which we like to do, there's actually Gaussian distribution with the particular mean and variance, can be provided as the following posterior distribution by using a Gaussian identity, the same equation that I used before. This Gaussian identity, please check it. If necessary, I'll post some background appendix on the website. So this one given training data capital X and capital Y, okay, and then we like to examine the output in response to X star. Okay, so this is the output, right? And then this guy, because the noiseless, so I just put in the F instead of Y star. So this one has the mean value of this and then covariance of this. Mean value is given by this. So this is the part we can actually derive from the previous case, and I just replace some of the covariance, inner product or quadratic form, that turns out to be kernel functions are put into this form, and then we can rewrite the previous case in this form. So given that this as basically posterior, and prior distribution characteristics of the prior distributions, we can apply to that Gaussian identity, and then now we can discuss the conditional distribution conditioned by X and Y, and then x star, we can find the means and the covariance in this way. So somewhat similar to the previous expressions. And now we're using this kernel matrices involved in this prior into this. So remember that the estimation of f as originally prior distribution is this one, this particular part of kernel. This is the before we incorporate the training data, our original estimation is basically having this variance, which is actually sitting here. Now it is reduced by incorporating x and y, which is involved in here, the second term. This is the one by incorporating the training data, we can reduce the variance from this value to this value. Okay, so this is something we gain by training the Gaussian process with the data points. Now, on actual case, having some kind of a noise superimposed, so covariance y is through a noiseless part plus this observation measurement noise part comes in, and that's all the change we have to make. So now noisy case, and we replace this part, and that's the only change we have to make. Then finally, given XY training data, and then we like to investigate what is the actually response in response to X star, what is the output F star, and then that's actually given by this expression. Only difference is previous case is this one was just a KXX, now KXX plus the sigma n square inverse. That actually makes this one a little bit bigger. Okay, same thing here. So if you plot that confidence interval plot x versus fx, it is a little bit expanded. Mean value is shifted a little bit, and actually the covariance is basically expanded. If you look into this part, in the previous plot, this yellow band was 0 at these sample points. Because the measurement is perfect, measurement is noiseless, it's actually going to this. But with the noisy measurement, this one is departing from here, and even this point is to have some uncertainty over here. So interpretation of the this predictive mean. So this is actually conditioned by such and such, and this is the mean values, right? So now this one, it can be interpreted very nicely. So this particular block of the kernel matrix having these components, right? Components, and remember it's a graph matrix, so we take all combinations of the elements involved in X and capital X, and let's think about the single X star, single X star. So single X star times versus X1, and a single X star versus sample point X2, blah blah blah, up to total n sample points. You can create this long row vector, right? And multiplied by this, and then you can get this expression. But let's look at this particular part. These are not the function of X star at all. So after you train the Gaussian process, this particular part is already determined, known. So I just replace this part by a vector, because the dimension is basically capital N dimensional vector. So I replace this one as alpha 1 to alpha n. It turns out that this guy, this times this alpha, we can write it as a linear combination. So mean value is given by the linear combination of all these kernel functions evaluated at the x1, x2, xn with the new the point we like to investigate X star. So what this means is something like this, as shown in the right here. So these are points that we measured, okay? Training data is used at this point. And now we like to investigate what is actually, output, here, corresponding to X star. Well, it may have some kind of, uncertainties, but we can certainly use the effect of, the result of X2 and X1, X3 used for training, right? And as shown here is a kernel values. Kernels in some way, it represents how close these data points are, how similar they are. So in a sense, this particular one, K, X star, X1, it's to evaluate the kind of similarity between X1 and then X star. And then this one is to be also influenced by X3, and then this particular kernel is to evaluate how close they are. And then interestingly, the prediction at this point, the mean value, is a linear combination of these actually kernel values, which are basically representing how close they are. So this is a really neat result, and the result is very much interpretable, transparent. Recall that the kernels represent how similar or close two data points are, okay? Depending on the nearness, the contribution from each training data point is evaluated and putting together like this, okay? So I like to conclude the, Gaussian process model is a nonlinear, non-parametric, and then probabilistic model. And the GP predicts output in response to test points as a conditional Gaussian distribution with mean and variance, okay? The GP variance is expressed as a kernel matrix, okay? Kernel matrix is a very important technique. And then posterior mean, this expression is given by a linear combination of kernels representing the nearness or similarity between a test point and the train and the data points which we use. Some of the drawbacks and something of which I haven't talked about also noted at the end. It is not effective for large data, since in the middle we have to take n by n matrix inversion, right? So data points up to several hundred and up to 1,000, it's okay. We can take the inversion very nicely. But if you have millions of points, this method in its original form is not applicable. So people, devise some way of alleviating this problem. So, they do some kind of pre-processing. Some of the data points are basically grouped together. So the net data points used for training is to be reduced to up to 1,000 points, and then they do this training. Okay, and I did not mention some of the hyperparameter tuning, such as the length scale L involved in radio-based function, kernel functions, and all that can be tuned depending on the nature of your problem. There are a few other parameter values involved and hyperparameters involved that can be tuned depending on your needs. So that's most of the things. So I think it is impossible to follow the all maths, but I hope you can capture some of the essence of this powerful method, Gaussian process, right? And we've been discussing the kernel functions, and kernels. This concept has had a pretty big impact in both the machine learning areas and the system dynamics and controls. Well, system dynamics, they could use this method more. It's been a little bit slow going, but I know it is actually very powerful tools to beat the linearity requirements. Most of the system identifications that we did as established, and techniques have been very well established for linear case, right? But this Gaussian opened the door to nonlinear identifications and non-parametric representation. Even though we have some hyperparameters, that's the high level parameters which you can tune, but I know bottom line is that it's non-parametric representation. We don't need to assume this may be a second order system to the third order stuff. We don't have to do that. Yeah, so that's actually a very powerful tools. Okay. Oops, one questions. Yep. Okay. This is actually a good question. And you have asked, since the kernels are positive, how can they be used to capture negative correlation between x and x something? Well, there's actually little confusing things. Positive value of correlation versus actually positive definiteness of the kernel matrix is a little different. So any elements involved in the matrix may be negative, but we have to make the matrix as a whole to be positive definite. Yeah. So if you check that one more carefully, you can find the reasons. They are different story. Yeah. Okay, I gave you the assignments. These are assignments, right? So this is the last assignments. So first one is very simple, and the second one, problem 2. The problem 3 is related to today's the talk, and this one we deal with this very simple case of radio based on functions. And I want you to draw that in a plot, all right? So this is kind of confidence interval, sectors involved, but it's more theoretical questions are also involved. So all very theoretical questions are put into some extra credit. So don't panic, please. But if you have some difficulty in solving this, I'm more than happy to help you. And then I plan to join you at this Friday's study group meetings. That's actually we'll discuss these stuff, which is a little bit challenging. Yeah, it's a little bit challenging. Yeah, because of the heavy mass involved. Okay, but and other than that, it should be all right. Yeah. Any other comments? Anyone has been exposed to Gaussian process in your research, or you have heard something about this, or you
We're starting to look at them.
Excuse me?
We're starting to look at them for adaptive control.
Oh, yeah. Right. Or many groups are using this. So maybe you attended your group's research meetings, and then your friends, your peer, researchers, and presenting something using the Gaussian process. You have no idea of what being discussed, but now it's all set. You understand the things, well, okay. And particularly interesting to me in my group, and we've been using this in combination with the unscented common filter. It turns out to be very powerful tools. So yeah, and then the good thing with this is that we don't need too many data points, and several hundred points up to 1,000. That's a reasonable amount of data, right? So it's not appropriate for extremely big data error. So, but other type of method, this one fits pretty well. Okay, with that, amazingly, I finished this, heavy materials in 90 minutes. So maybe you need to review this more, but I hope you can get to something about this important concept. Okay, we'll see you this Friday. Yeah, have a good one.
Thank you.
Bye.
Thank you.